light inextensible string of length 5 meters is attached to one end of a fixed point P. Alright, let's put P here, which is above a smooth horizontal table. So P is actually up here, and this is directly below P. Is everybody cool with that? And what we know is that it's coming down 4 meters above. Alright, and it's attached to the red particle. And what weight's the red particle? 5 kilograms, is that right? Actually the weight would be 5g, but it's the 5 kilogram red particle, okay? It's on a table, is that right? So because it's on a table, I'll need a parallelogram. There's your 3D table. And once again, it's doing circular motion in a circle. So the helicopter point of view, if you're directly above it, is that it's a perfect circle. Is that okay with you guys? Now, okay, so we know that this is 4. We know that this is 5. I think we'll be able to do Pythagoras' theorem to find out the radius of the circle, won't we? So everybody knows it's a 3, 4, 5 triangle. Okay, so you get the 3. Now, the tension is, which way is the tension working? Would you agree it's all going diagonally left up? Because the hypotenuse is the string. Okay? The string is 5 meters. It's 4 meters above the table. The other end of the particle is attached to 5. So the other end of the string is attached to a mass of 5 kilograms, which moves in a circular table. If the speed of the particle, so we know that phi equals 3. Okay? So let's find out. Let's find out what we need here. All right. We should probably resolve the tension into its components. So up has to equal down, correct? So we can do a bit of up versus down first if you want. Alright, so let's do up versus down. Alright, so guys, here's the tension. The tension is going diagonally left up. Alright, and let's call it T. Alright. Now, call this angle X, if that's okay with you guys. Can anybody tell me what's cos X and tan X? Cos X will be, anybody? Adjacent over hypotenuse? Grant. Sin X? Okay, awesome. What does that mean about the adjacent components? It's T cos X, otherwise known as 3 over 5 T. And what about this? What about the other version up here? Anybody? Does the opposite? 4 over 5t. Is that alright? Now, we're going to do up versus down to start off with. Okay? And reaction force. Or is it in contact with the table? In a circle on the table. Which means that it's actually in contact with the table. Fair enough, right? So up versus down. What's going down? Everybody happy with 5g? 5g directly downwards. What goes down equals what goes up. So what goes up? 5g. 5g goes down. The reaction force R goes up. Now R doesn't equal 5g, and I'll tell you why. It's not supporting its full weight. In the last question, R was supporting the full weight, but you can also see that there's a tension component going upwards as well. See that tension component? So that means that R isn't supporting all 5g, it's going to be R plus 4 over 5t. That's also going up. Is that alright? Now the next equation we're going to work on is the left-right equation. And what did we say earlier? It's going to be the central pedal. It's going to be the central pedal force equation, okay? Now, first things first. What's the only force that works left to right? What's the only force that works left to right? 3 over 5 t. Alright. So 3 over 5t equals, now our m value, lads? 5. Our v value? 3 squared. And our r value? What do you reckon? R value of 3. Alright. So lob them in and see how we go. So what do you reckon? I think the two 9s on either side will cancel. I think we're going to get t equals 25. Alright, just check it here. Yeah, t is 25 newtons. Okay, and that means we can calculate the r value, can't we? Now the r value will be smaller than 5g because we know that it's aided by the t value. 5g, what's 5 times 9.8? Is it 49? Let's go with 49. And that's 20. So the reaction force should be 29 newtons. Is that okay with you guys? Alright lads, will you guys give 4 and 5 a go for a second? Start with 5 and we might have a go at 4 in a second. Alrighty, particle mass m moving with constant speed in a horizontal circle which is on the inside surface of, oh, it's a different type of one. Sorry, my bad, I set you up with a bad one here. Should have read it before I left. Alright, so it's a sphere. Have you ever seen a motorbike rider on the inside of a cage? Have anyone ever seen it? Alright, and you notice that the motorbike rider can essentially stay at the same height all the way around the inside of the cage. Alright, they're just doing perfect circles, okay? So this is essentially what this is, that it's going so fast that its force is keeping it up, keeping it supported, okay? So when that motorbike driver actually does that trick, he has to keep the velocity exactly the same. What happens if the motorbike driver accelerates? What will happen? He'll actually start to ascend the inside of the dome, and if he decelerates, he'll drop. Okay, so that's the cool thing about the trick. Should probably show you a video, but yeah, you never know. We'll see in a minute. All right, so that's how I always remember this one. Okay, the next thing, smooth sphere of radius. So I'm assuming he's sort of below the centre of the sphere, if you get what I'm saying. I don't know if they can go above the centre of the sphere. I don't think that's possible. Once again, I'll look it up, but I don't think it's possible. So I think he's there. We're going to put the particle down here, or the motorbike driver down there, and we're going to say that he's travelling along this circle below. It's below the centre of the sphere. Is that all right? So what we can do now is we can sort of make a triangle out of this, like so. Now, what do you reckon, lads? That's 5, isn't it? That's 13. So what do you reckon about the radius of the circle? 12. So the radius of the ellipse or the circle is 12. Okay. So it means you're doing circular motion, radius 12. All right. Now what else does I want to know? Show that the speed of the particle is 16.8 meters per second. Alright, so let's see what forces are at play here. Now, something that we learnt in connected particles is the following. Very simply, 8 kilograms down, which is 8g, what would be the reaction force R? Anybody? What's the reaction force R? In this case, just this really simple case here. R is also HG. Why is it HG? Yeah, it's staying put. Right, so everything up equals everything down. Now we move to a more a staggered one, where it was like this. All right, and what happens to the R value this time? So if that's 8 kilograms again and it's HG directly down, what happens to the R value? The R value is perpendicular to this surface here. Do you get what I'm saying? R value is perpendicular to the surface it's in contact with. So in this case the R value will be diminished because the R value isn't supporting the full weight. Why is it not supporting the full weight? Because the particle is slipping at the end of the day, isn't it? Alright, now that brings us to the a circle or a sphere. Guess what happens to the R value? Remember we said R value has to act perpendicular to the surface it's on. So any circles or any spheres. Okay, so any circles or any spheres. If I'm here and I have a weight of, let's say, 8g again, the R value is always perpendicular. And because it's perpendicular to technically a tangent point, it has to go through the centre of the circle. So your R value always aims back up towards the centre of the circle. So, in this case, here's our particle, and there's our R value. So we're going to resolve R up and down. Okay, so what do we say cos x and sin x there? Anybody? Cos x? 12 over 13. Sin x? What? 5 over 13. Okay, our R values. What do you reckon? R cos x and R sin x? 12 over 13 R. The 12 over 13 R is what drives the horizontal circle. Now up versus down, what do we say there? 5 over 13 R going up. Now we're going to do what we did last time. What goes up equals what goes down. So what do you reckon? What's going downwards? What's the weight of the particle? Mg. So mg going downwards is equal to what? Anybody? What goes downwards here? Or so what's going upwards, I mean? Yeah. So mg going up, mg going down is equal to 5 over 13 going up. Alright, what formula do we use for the the circular motion again? What's it called? F equals mv squared over r. And this is the what's the only horizontal force you have there? What's the only horizontal force you have? Exactly. So your 12 over 13 r is supporting your mv squared. So m we don't know. V squared is 16.8 squared. And radius is 12. We all cool with that? Okay. Oh, sorry, I'm wrong. I'm not allowed to use 16.8. I need to show that it's 16.8. Be careful never to make that mistake. If you're asked to show that it is, you're not allowed to use it. Alright. Now, I'm going to sub out the R. Does everybody see the R? I'm going to get R on its own here. And R on its own is going to be 13 mg over 5. Is that okay? And then what do we have here? 12 over 13 R by 13 mg over 5 equals mv squared over 12. Now the m's will cancel. 12 times 12 is 144. What's 144 divided by 5? 28.8. Multiplied by gravity, which is 128.282.24. So for those who wondering what I did, I moved that 12 up here, I multiplied it out, and I subbed in gravity as 9.8, and I got 282.24. I'm going to square root that now, and I get 16.8. Is that okay with you guys? Alright. So that's 3. Yeah.
What's the reaction force measured in?
What's the reaction force measured in? Oh, yeah, newtons, yeah. So a marble of 10 kilograms is describing a horizontal circle on the inside of a smooth sphere. Alright, so it's similar to the one we did earlier. So your marble's here, the centre of your circle is here. and it's doing a, what's it doing? It's doing circular motion at the bottom. Okay, the radius of the sphere is 1.3, so there's 1.3 right there. It's 0.5 below, so the purple dot is the center of your circular motion. That's 0.5. Pythagoras' theorem will tell us that the radius of that circle is 1.2, won't it? Because it's a right angle triangle, so it's 1.3 squared equals 0.5 squared plus r squared. R squared equals 1.44. 1.2 equals r. Okay, so 1.2 meters. Alright, next thing. Now, the normal reaction is the R value, and as you said earlier, that the R value is acting along the radius, has to act through the centre of the circle, so your R value is always perpendicular. It's like a tangent, it's perpendicular to the tangent point, alright? So we know our R value is going in this direction here. We call this angle X. And angle X is 0.5, 1.3 and 1.2. Cos X will be 12 over 13. Something like that, yeah? Oh! Sin X would be 5 over 13. I'll pause here. Did I have a lot? So everybody happy with the 1.2? Alright. And everybody happy with 12. Now, the reaction force R, because we have this information, we can now say that the reaction force R, which also acts along this angle X, that's reaction force R, and this would be R cos X, and then R sin X. Is that okay with you guys? And that would be 5 over 13 R and 12 over 13 R. We are so far? Now, what goes up has to equal what goes down. So what goes down? What weight is it? 10 kilograms? So 10 G, okay? So 10 G going straight down. Okay, so 10 G going straight down. So it's going to be 10 G going straight down equals 5 over 13 R going up. Okay. And then the next one is going to be the centripetal acceleration, which is mv squared over r, and it has to equal 12 over 13r. Alright, does it give us any more information? It doesn't give us the speed, and it doesn't give us the angular velocity. Okay, let's find out what we're going to do here. Alright, we know the r value is 1.2. Oh, sorry, that's capital R. Excuse me. Capital R, small r. We know that small r is 1.2. We can isolate capital R using the top equation. R equals 130 G over 5, which is 26 G. And 26G, 26 multiplied by 9.8 is 254.8. Alright, so now we get mv squared. Now we know the m value is 10, so it's 10v squared. 10v squared over 1.2 equals 12 over 13 times 254.8. So it's going to be 12 over 13 times 254.8 multiplied by 1.2 divided by 10 to get my v squared. So let's see what happens here. 12 over 13 times 254.8 multiplied by 1.2 divided by 10. Then we get 28.224 for, oh sorry, that's v squared, isn't it? And when you square root that,
5.3126.
huh? Oh, 5.3126. Everybody get that? You got that, Mick, did you? Meters per second. Now, the question did ask us for the reaction force, didn't it? Oh, we already got that. Never mind. Reaction force is obtained. And, yeah. Now, as for the angular velocity. Now, what we have here, guys, is we have this marble is running a circle, okay? And once again, there's not an ellipse, it's a circle, just sort of a 3D perspective. The marble is on the inside of a sphere and it's currently going 5.3126. Its speed is always like a tangent. Its speed is always perpendicular to the surface. Sorry, perpendicular to the radius of the circle it's on, alright? But it's cutting an angle, isn't it? What happens every second? Every second it's travelling, what's it, 5 meters, isn't it? 5.3 meters. It's cutting an angle every second, okay? So how do we change that into angular velocity? Does anybody remember? V equals RW. W equals V divided by R. And what Mick said is just divided by, what's it, 1.2, is it?
Yeah.
And what you get here when you're done?
4.47.
4.47? Rad. What?
27.
4.27. 4.427 radians per second. Is that okay? Now, for homework tonight, what we're going to look at is, we have a couple of these questions to do. So we're going to do, they're on my YouTube channel. If you're to be stuck, I'll upload it onto Google Classroom pretty soon. But we'd obviously like us to have a go at 2, 4. Did we do 6? I don't think we did. 6, 8, 10, and 11. Okay.